So where we are now is section 9.2, page 620, and the second of our conic section shapes is the parabola. So again, we have only ever looked at parabolas from the quadratic equation point of view. Now we're going to look at them from the conic section point of view. We're going to look at how parabolas are actually created, how they're generated, which is something you guys have never really talked about before. So the first thing I want to do is I want to show you where parabolas come from in terms of, I think that's the one I need, in terms of slicing a conic. So here's our conic, our double cone again. And so what we're going to do is we're going to slice this at an angle now down one of the lobes with our plane. And as soon as that falls away, it's a little bit slow, guys. Sorry, I need to re-render this so it's not quite so fuzzy and not quite so slow. But when it turns, you guys are going to see the purple parabola shape, which is our cross-section. So that's where a parabola comes from. Okay? If we change the angle of that plane a little bit, then we will see the shape of the parabola will change a little bit. It can get skinnier, it can be wider. If we move the plane closer to the edge when we come down to cut it, okay, it'll also have an effect on the shape of the parabola. So that's where parabolas come from, okay, in terms of being a conic section. So what I want to do now is I want to talk about the definition of a parabola. And a parabola is the locus of points. And again, what does locus mean? Collection. Good. The collection of points in a plane such that each point is equidistant from a line and a point not on that line. So what we have is we have a line, and we have a point that's somewhere but not on the line. And what we want to do is we want to find all the points in the plane that are the same distance away from the point as they are from the line. Well, there's a real obvious one exactly in the middle right here. So somewhere here there's a point, right? Also, because this distance is the same as this distance. Somewhere over here we have a point where this distance is the same as this distance. Remember, distance to a line has to be perpendicular. Somewhere over here we have a point where this distance is congruent to this distance. Somewhere over here we have one where this is congruent to this. You guys get the idea? And what happens is when you string all those x points together, you end up with a parabola. Okay? We have names for that special point and that special line. The line is called the directrix. So the word direct with an RIX at the end. The point is called the focus. So this is our directrix. This point here is our focus. Okay? And parabolas have very, very special mathematical properties. It's not just any old U-shape, guys. They have actual properties. One of the things that's special about a parabola is that if you have a parabola and its focus, it turns out that anything that comes down parallel to this axis of symmetry, you guys remember the axis of symmetry running down through the middle of it? Anything that comes down parallel to the axis of symmetry is going to bounce off the parabola and end up going right to the focus. So if we have one coming down like this, it's going to hit the parabola and it's going to bounce to the focus. It's going to come down, It's going to hit the parabola. It's going to bounce to the focus. Likewise, if you shoot something out from the focus and hit the parabola, it's going to bounce parallel to the axis of symmetry. Because of these properties, parabolas are used for satellite dishes. Satellite dishes are typically parabolic dishes. It's the cross-section of a parabola. Okay? Because they have this property. What's sitting on a satellite dish typically suspended out over the middle of the dish? A what? Well, it's a focus point, but what's actually on a satellite dish typically suspended out in front of it like that? It's usually a little box, right? And what is that box? That box is either the transmitter or the receiver, depending on whether it's a dish that just receives or one that transmits, right? So this way you can take this thing, you can aim it at a satellite, you can transmit from the focus out to the dish. The dish is going to reflect it all in essentially a straight beam so that you get a good strong signal going up to the satellite. Likewise, anything coming down from the satellite that's coming down straight towards the dish is going to be a very strong signal that gets reflected and collected at the focus. So this is one of the applications. Okay, there are other applications of parabolas as well. One of them I'll share with you is many, many years ago, I used to work for an indoor shooting range. Anybody ever been to an indoor shooting range before? Okay. Indoor shooting ranges have backstops to stop the bullets after they go through the paper targets. And typically, most backstops will look like a slanted piece of steel. Problem is, it's not a slanted piece of steel because what would happen is the bullets would come in, they'd hit this piece of steel, and where would they bounce? Straight up through the ceiling and put a hole in the roof. And every time somebody shoots something, you're going to end up with another hole in the roof. Probably not a good idea, right? So what do they use instead? Well, there are a couple of different ways around that problem, but one of the ways is to not use a straight linear backstop. What you use is you use a parabolic backstop. There's a slight curvature to it, and not just any curvature, it's a piece of a parabola. It's like looking at this slice of the parabola. And what happens is when the bullets come in, they hit the parabola. Because it's not the full parabola, what's going to happen is it's going to bounce up this way, and it's going to hit again. And then it's going to bounce up this way, and it's going to hit again. And it keeps bouncing and skipping until it gets to the top. And then what you have is you have plates that are overlapping kind of like this, and the thing spins around and around and around until it loses all of its velocity, and then the piece of lead just slides down the face of this into plastic collection cups at the bottom. Without that being a parabola, you would never be able to do that. Okay, but that's one of the properties of a parabola. So those are some, I think, interesting applications of parabolas. Okay, so let's take a look at a parabola actually being constructed so that you can actually see, whoops, sorry, wrong program. Let's go to Sketchpad. So here is my directrix, my line. F is my focus. It's my point not on the line. This point D is an example of one of those points where this distance is the same as this distance. So notice the distance from F to D, right, from here to here. Sorry guys, let me restart my tablet. It's falling asleep on me here. So notice the distance from F to D is being measured at 2.07 centimeters. And the distance from D to the control point, which is a point on the directrix, is also 2.07. As I move this control point, D is going to move to keep those two distances equal. And you'll see the numbers change, but you'll see these two distances are always the same. And so by dragging this around and looking at all these points, we see the locus of points that's created. And so as these numbers change, you see that they're always kept equal to each other. So there's our locus of points, and when we fill those in sufficiently, we get our parabola. Everybody see how that works? That's how a parabola is actually generated from the focus and the directrix. How do you change the shape of the parabola? You move the focus relative to the directrix. If I move the focus farther away from the directrix, I get a wider, flatter parabola. If I move the focus closer to the directrix, I get a narrower, skinnier parabola. So does everybody see how those two objects generate this shape? Now, you're not going to be generating these, but I wanted to show you that this is a mathematical construction, okay? This is not some theoretical object. We can actually construct this thing to make perfect parabolas. All right. Let me get rid of this. So now what I want to do is I want to take a look at what you're going to be actually expected to do. So, with parabolas, first of all, remember that we're just learning the basics of our shapes. And so I told you that all of our shapes are going to start out anchored at the origin at 0, 0. So when we look at our parabola, what's going to be anchored at 0, 0 is this point right here, which is the what? What's that point on a parabola called? The vertex. And what's the line that runs down the center of the parabola this way called? Axis of symmetry. Okay? The vertex is always going to be 0, 0 for this section. We're not going to start moving it away from 0, 0 until later, after we've examined all the shapes, the basic properties of the shapes. Everybody with me on that? So, we're always going to be dealing right now with our vertex at 0, 0. With your vertex at 0, 0, it gives rise to two different basic general standard form equations of our parabola. And which equation you're going to be working with depends on which way the parabola opens. There are 4 possible directions that the parabola can open. We can have parabolas that start at the vertex at 0, 0 and open upward. There are parabolas that start with the vertex at 0, 0 and open downward. Okay? Notice those are opening in which direction? The x direction or the y direction? The y direction. They're opening up or down. That's the y coordinate direction, right? Everybody sees that? Okay? We also have parabolas that either open to the right from the vertex at 0, 0 or open to the left from 0, 0. Which direction are those opening in? The x direction. They're opening left and right horizontally. As long as the vertex is at 0, 0, our equations for these are going to be x squared equals 4py. This is a form of the equation you have not seen. You have only worked with y equals ax squared plus bx plus c, or vertex form y equals a times x minus h squared plus k, or intercept form y equals a times x minus p times x minus q. You guys have not worked with the conic section version of the parabola equation. This is new to you. X squared equals 4py. I'll talk about what the p is in just a moment. Notice, guys, which direction did these parabolas open? The two on the left? Which direction, x or y? Y. Where's the y in the equation? No, where is the y in the equation? Yeah, it's with the 4p, right? And notice, is the y being squared? No. So the 4py, this is the direction that it opens. Does everybody see that? It's not which letter is being squared, it's which letter is attached to the 4p and is not being squared. That's the one that tells us which direction these open. Everyone clear on that? So what do you think the equation of this one's going to be? Exactly. Y squared equals 4px. This is the direction it opens. Okay, so make sure you have that down. Now, the reason that there are no other numbers being squared with the x and the y, well, with the x or the y, I should say, and there are no other numbers attached to the x in parentheses or the y is because our vertex is 0, 0. When we're no longer at 0, 0, there will be other numbers that come into the equation. And we'll see those next week. Okay, let's take a look at an example. You have a question? No. Okay. So here's an example. We have x squared equals 16y. So take a look at this, guys. Which way is this thing going to open? The y direction. So it's going to be up or down. We don't know which way yet, but we know it's going to be either up or down, not left or right, because the y is on that right side by itself. So now here's the thing. What does the p have to do with anything? So let me go back to this picture, and let me clean this up just a little bit. I want to get rid of the stuff that I don't want to look at. I want to leave the stuff I do want to look at. What P represents, guys, is the distance from the vertex to the focus. This is P. Okay? Everybody see that? That's the distance from the vertex to the focus. It turns out that the distance from the vertex to the directrix also has a length of P. But technically, we're going to actually think of this one as negative P because it's P units, but in the other direction. Everybody see that? So if from the vertex we go up to the focus, then from the vertex we go down to the directrix, the same distance. So if we went up to the focus, we have to go down to get to the directrix. Everybody see that? Now, here's the thing that I need you guys to understand. Which way did this parabola here in this drawing open? Up. Where's the focus compared to the vertex? Up. That's what determines which way the parabola opens. The focus is always on the interior of the parabola. In other words, your parabola always curves around your focus. And it's very, very important for you guys to understand that because we're going to have foci. The plural of focus is not focuses. That's the plural of focus when focus is a verb. When it's a noun, it's foci, F-O-C-I. We're going to have foci on the rest of our shapes as well. And the thing that you need to understand about all the different conic sections, they always curve around their foci. Always, always around their foci. So the focus has to be on the inside, the directrix is on the outside. Now, notice that when this thing opens up, the directrix was horizontal. Do you guys see that? The reason is that the directrix is never allowed to touch the parabola. If I drew this directrix vertically, no matter where I draw it, because our parabola gets wider and wider and wider, do you guys see eventually they would crash into each other? That is never allowed to happen. Okay, the directrix cannot touch the parabola, and vice versa. Otherwise, it causes our parabola to basically collapse down to a point. So, let's go back to this now. So if I'm on this picture, where's the focus going to be compared to the vertex? Above or below or left or right? It has to be above. The focus is going to be up here. The directrix then would have to go like this. Where would the focus be on this one? Below. Where would the directrix be? Above, going which way? Horizontally or vertically? Horizontally, right? Otherwise it would crash into the parabola. Where would the focus be on this one? To the right. Where would the directrix be? To the left, and it would have to be what kind of line? Vertical line. Otherwise it would crash into the parabola. Do you see that? Where would the focus be here? Left. Where would the directrix be? Vertical or horizontal? Very good. Do you guys see how basic that is? Not rocket science, right? Although this is used in rocket science, but it's not rocket science. Okay, here's what you now do to figure out what's going on. Notice our x squared is accounted for in our equation. And I like to write the equation right above it, the general form of the equation, the standard form. This is standard form. Notice the x squared is already in the equation, the y is already in the equation. The only thing that's not accounted for is the 4p. So what must the 4p be in our actual example? 16. Do you guys see that the 4p must be the 16? So what we do is we write that down. 4p is equal to 16. Anything hard about that? What is p equal to then? So p is equal to 16 divided by 4, which is 4. This is very important. This is going to help us draw the graph and find our focus and things like that. Now, what's very important to understand, guys, is p is the distance from the vertex to the focus. If p is positive, that means we're going to go up from the vertex to the focus. If p is negative, then that means we're going to go down from the vertex to the focus, and the thing's going to open down. Which of these is positive P? If P is positive, the thing opens to the right. If P is negative, it opens to the left. So does everybody see that? Up and right are positive. Left and down are both negative, just like you'd expect, just like your x and y axes. So since P is positive 4, which way is this going to open? Up. Because it's going to open in the y direction, and it's going to open up because P is positive. So when we go to draw the graph of this, let me show you how this works. There we go. So we know our vertex is where? No, our vertex. 0, 0, right? Now, which way did we say this is going to open? Up. What I want you guys to do is very lightly just put a quick, like, generic kind of parabola in there, just to remind you that it opens up. Now we can see from that which way are we going to have to go to get our focus? Up. How far? 4 units. So from the vertex, I'm going to go 1, 2, 3, 4 units up. There's my focus. What are the coordinates of my focus then? Because that's one of the things they're going to ask you for. 0, 4. Everybody see how easy that is? Once you know which way you're moving. Now, if I went up 4 to get to the focus, where do I go to get the directrix? Down 4, right? 1, 2, 3, 4, which means the directrix is 0, -4, right? No, 0, -4 is what kind of object? It's a point, right? What does the directrix have to be, though? A line. So what should it be? Which is it, x equals or y equals for horizontal? Well, which axis does it cut across? Cuts across the y-axis, so it's y equals -4. Your directrix is always going to be either x equals a number or y equals a number. If it cuts across the x-axis, it's x equals, vertical. If it cuts across the y-axis, it's y equals, horizontal. This one's horizontal. Everybody clear on that? Okay. The last thing that we're going to do here, guys, is we're going to actually draw the real sketch. This was just a generic parabola that I put in. Now, you can draw the directrix if you want. They're usually not going to ask you to actually graph the directrix. If they do, you can put it in, but you don't have to. That's not really part of the graph of the parabola, but we can put it in if we want to. But don't feel like you have to if they don't ask you for it. They're typically going to ask you just to draw the parabola. So what can we do now to draw the actual parabola? We can plug in numbers. We can make a t-chart, right? And plug in values for x and y. Is that acceptable? Yes. Will it take you very long? No. Is it hard? No. But let me show you another way to do it that I think you guys are going to like better. You do not have to use a t-chart to graph these. There is an object with regard to parabolas that is called the focal width. The focal width tells you how wide the parabola is through the focus. So does the name make sense? Focal width is the width of the parabola drawn or measured through the focus. Here's our focus. It turns out that the focal width is always the absolute value of 4p. Where did 4p come from? It's part of our equation, right? Remember, guys, I told you to write down 4p equals 16? Did you guys really have to write down 4p equals 16 in order to figure out that p was going to be 4? No, you could have just looked at this and said, oh, look, p is 4. But I told you to write down 4p equals 16. Why? Because we use it in our equation. If 4p is equal to 16, then the focal width is equal to the absolute value of 4p, which is the absolute value of 16. Why the absolute value? Because sometimes p is negative, and the focal width is a length. It has to be positive. So essentially, we just ignore the negative. That's what the absolute value is there for. This is 16. What does that tell us? That tells us that our distance from one side of our parabola to the other through the focus is 16. If this parabola is supposed to be 16 units wide, then starting at the focus, how far am I going to have to go each way? 8. Do you guys see that? If we want the whole width to be 16, doesn't it have to be 8 each direction? So you don't start at the vertex, you start at the focus and you count over. 1, 2, 3, 4, 5, 6, 7, 8 to the right. 1, 2, 3, 4, 5, 6, 7, 8 to the left. And this is the actual parabola. Oops, sorry guys, I missed a little bit. Let's fix that. Do you see how easy it is to graph the actual parabola? We don't even need the t-chart. We're done. There's our graph. You guys like that better than a t-chart? Quick and easy, right? Especially since you've already figured out what 4p is. All you have to do is cut it in half and go that far each way from the focus. Any questions about that? Yes, sir. That's p. From the focus to the vertex is our p. That was this 4 units. P is the distance from the vertex to the focus. Yeah. All right, guys, questions about that before we do one more example? We'll do it quickly. Anybody know offhand what time we're out of here? Is that what it is? Let's check. I have it here. We are out of here at 2:13. Okay, let me show you guys how quickly these can be done. You guys with me? Okay, stay focused because I'm going to go fast. If you have questions, you can ask me afterwards. But let me show you. What happens if we have y squared equals 12x? Well, first of all, which way is this going to open? Yeah, we know this thing is going to open sideways in the x direction, right? So either left or right. So this is our y squared equals 4px. So what is our 4p equal to? 12. So write down 4p equals 12, which makes p equal to what? 3. So I'm going to get my graph. My vertex is where? Because they're always 0, 0 on these right now. We'll change them later. Not today, not this section. We said this is going to open either to the left or to the right. Since p is positive, which way is this going to open? To the right. So I'll tell you what, guys. Let's change this. Let's make it negative 12x so we can see what happens if it goes in the negative direction. So now 4p equals negative 12, which makes p equal to negative 3. So which way is this actually going to open, left or right? So this is going to open which way? Left, in the negative direction. Okay? So I sketched this in really lightly just to remind me, which way am I going to have to go to get to my focus then? To the left. How many units? 3. So we're going to go 3 units in the negative direction. There's our focus. So what are the coordinates of the focus then? Good. Negative 3, 0. If I went to the left 3 to get to the focus, where do I go to get to the directrix? To the right 3 from the vertex? Which way is the directrix going? Yeah, up and down, right? So there's our directrix. What's the equation of the directrix? Good, x equals positive 3. One thing I didn't mention on the other one, guys, what's the axis of symmetry going to be? What's our equation of the axis of symmetry, the line that runs right down the middle? Good, y equals 0 on this one. What would it have been on the last one? X equals 0, right? It's always either going to be x equals 0 or y equals 0. Why? Because our vertex is at 0, 0. So it's got to go through 0, 0. It's either vertical or horizontal. Now, that won't be the case later on when we move these, but right now it is. It's pretty easy. Okay, the last thing we have to do is draw it, the focal width. And again, you don't have to do it with the focal width, but it's a nice way to go. That's the absolute value of 4p. What was 4p equal to? Negative 12. What's the absolute value of negative 12? 12. So if the width of this through the focus is 12, how far do I have to go each way? So I'm going to go from the focus up 6, and from the focus down 6. And here is my actual graph. You have to draw the actual graph, guys. And then what you should really do, I didn't do it on the last one, go back and then erase that little sketch that you put in so it doesn't get in our way. There we go. We're done. So when you understand how this process works, do you guys see how quick these problems go? There's not much to them. Now, I'm explaining it to you the way I'm explaining it to you because later on, when we start moving these around, the process is going to be the same. The only thing that's going to be different is instead of starting here, maybe you're starting up here. And you're going to sketch which way it opens, and you're going to figure out what P is so you know where to put the focus. You're going to do it exactly the same way. So we're not going to have to learn a new way of doing this when we start moving these around. We're just going to add a couple of more considerations to it. Any questions? Does that seem pretty doable? Okay, so let me get you the homework assignment then.